Welcome to Allen High School. We are discussing acid and base chemistry in our AP/IBHL1 class. Now, we're going to look at a very unique question this time. It's a titration, but instead of your typical titration, where we have the x-axis here and then we have the y-axis, and on the y-axis we'd have volume of acid or base, and on the y-axis, so x is volume, y would be pH. This time what we have is conductivity. And we have, and I wish I could draw better for you here, but we'll just deal with my little drawing. So this is supposed to be a burette. Now, we have our acid in our burette, and we're titrating into usually an Erlenmeyer flask, but maybe a beaker if we've got to fit a probe in there. We have our barium hydroxide. It helps to draw pictures sometimes of these things. Now, we have a strong base with a strong acid, so we're going to start at a very high pH. Actually, we're going to have a little bit of a sharper initial point here. It's going to be pretty sharp. It's going to drop at the equivalence point, and then it's going to go very acidic because we have a strong acid present. So we don't really have that gently sloping buffer zone that we have in a weak acid-base situation. Now, in this case, we're dealing with conductivity. Conductivity, remember, is the movement of electrons. And in order to have the movement of electrons in a solution, we need mobile or freely moving ions. In other words, we need an electrolyte. So let's see what's going on in our solution, that we have a strong electrolyte or electrolytic solution moving to a very weakly electrolytic solution to a strong electrolyte again. Now, question 1 says write the balanced net ionic. So I'm going to write the complete formula equation first. H2SO4 plus barium hydroxide. This is a neutralization. A neutralization, simply a double replacement. HOH together make water. And then I'm going to get barium sulfate. Now, whenever you're after a net ionic, it's important to pay close attention to states. Now, pure water is a liquid. These were aqueous solutions of. It says solution of is titrated with a molarity, which implies a solution of. So those are both aqueous. But if you remember your solubility rules, sulfate with barium is insoluble, so that's a solid. Now, I'm going to do my complete ionic. I want to just lay out more steps than I normally would. Now, H2SO4 is a strong acid, but only the first H plus is strong. The second H plus is a weak acid scenario. So that's how I would prefer that you write H2SO4. I'm going to break barium hydroxide into its ions. So I get barium ion plus 2 hydroxides. We're going to keep the water together, and we keep our solids together, if you remember from doing our double replacements. And this leads into our day when we have scheduled to talk about acid-base reactions and anhydrides, because this is very much just an acid-base predicting reaction. Now, at this point, we can delete our spectator ions. And lo and behold, there are no spectator ions, the way I teach you to write sulfuric acid. And so, that's it. My complete ionic is also my net ionic. So part A is done. Let's forge ahead. You should be able to grab some good points there. Now, this question says, explain why the conductivity decreases, passes through a minimum, and then increases. Now, if you remember, early on this side, we would have our H plus our HSO4 minus. Those are going to be in excess. Excuse me, I did that backwards. I'm so sorry. That's going to be our limiting. Up until the equivalence point, what we're titrating with is our limiting. And our barium and our hydroxide are our excess. Okay? Now, we're taking those two and forming a solid and pure water, neither of which will conduct. So, as we go down here, we're losing more and more and more. Let me get a better color. We're losing more and more and more of our barium and hydroxide ion. So as we are on the forefront of that, we are decreasing our barium ion concentration and our hydroxide ion concentration, and we're increasing the amount of barium sulfate and water, neither of which conduct. So that is point 1 on the forefront. Okay? Now, it's going to reach a minimum. At this minimum point here, we have exact ratios of H plus HSO4 minus and barium ion plus hydroxide ion. These all go to 0 and go 100% to our barium sulfate and our water. So it's going to reach a point. Now, you would have thought that we have no conductivity here. We're going to discuss that issue in a minute. So at this point, we have no ions from our acid or base. They are at the equivalence point. By definition, they are there in molar equivalence. So no ions from our acid or base. And our products don't conduct. Okay? So that's why it reaches a minimum. Now let's look at the upswing. After the equivalence point, what do we have? Well, we have excess of our H plus and our HSO4 minus. And the more excess we add, the more ions we get. So we start adding excess H plus HSO4 minus that have no base to react with, because it's done. We've passed the equivalence point. We have no base to react, and little typo there, or spello, I don't know what we're going to say. Oh, Dina. Mess up. Okay, to react with that, now I'm not putting this in AP words. These are my words. You could get much more elegant than this. But because we have these excess ions, we continually increase the concentrations of these as we keep adding more and more excess past the equivalence point, and therefore our conductivity increases. Okay, that was tough. That was part B, and that was, I think, pretty hard. This, in my mind, is a much higher order critical thinking skill than we often do. Part C, calculate the number of moles. Highlight that, underline that. We're looking for moles, not molarity. And it wants to know that at how much was originally present during the titration. Well, at the equivalence point, my number of moles of my barium hydroxide should equal my number of moles of H2SO4. That's the definition of equivalence point. Well, when we read on this, and we would have certainly, as I was grading this and AP is grading this, it certainly would have expected you to estimate this. They estimated it, frankly, right at 40. Okay, I see it at just a little past 40. So notice I angled over there a little bit. I would accept anything from 40, 41-ish, all right? So to get moles, remember molarity is moles per liter. So moles are equal to our liters times our molarity. So that's 0.04 liters times our molarity of 0.1. And so our answer would be 0.004, and I only went to 1 sig fig because that's all they gave us for our molarity, and we're estimating our volume here. So that really is the best we can do on that question. Now, let's go on to the last one. I think quite difficult, but if you think about what you have in solution, it will help you. So right there, that's the equivalence point. If you look back to your answer in A, the only thing we have in solution at this point is barium sulfate plus water. Now your book would have dealt with this after this chapter, but we've already done this. Now we have two things that can possibly go on with these. For one, water always slightly ionizes to form H plus OH minus. You're not going to get much though. This is small. Now, we also learned in our last unit that we can set up an equilibrium with what we call quote unquote insoluble salts. And so that barium sulfate would quickly set up an equilibrium. Remember our KSP equilibrium. So the net effect, and frankly, I prefer this answer, or really I prefer you see both. Okay, I'd have to know the KSP for barium sulfate to know which is the key factor involved here, but I would hope you would know from KSP discussions that whenever you have an insoluble salt, you still have a small amount of ion present. And if you have mobile ions, you have movement of electrons. If you have movement of electrons, you have conductivity. And I would include that in my answer. Ions allow movement of electrons, which is by definition conductivity. Okay, you want to mention that in your answer somehow, some way. Okay, we have more of these tough kind of higher order thinking questions to answer, but they'll always have parts. Always read every part of an AP question, because you may be lost at part A, but be able to grab some part points in part D. So you always want to look at every part of the question. So until the next one, this is signing off.